Okay, so the last time we looked at individual relations between one or two sets and what types of operations we can do on those relations. Today we're going to explore extending that to relations of more than two sets and how those work with databases, which is the topic that you'll see later on in the curriculum. So you can have relationships among elements of more than two sets. For example, student names, majors, and grade point averages. Or if you're in a medical setting, the patient, their age, their weight, underlying conditions, etc. So you can map things from more than one set to create a relation. And so N-ary relations are useful for representing computer databases, as I said in the introductory slide. So we'll let A1 through AN be sets, and an N-ary relation on these sets is a subset of the cross product of those N sets. The sets A1 through AN are called the domains, and the number N is called the degree of the relation. So let R be a relation on the set of the natural numbers crossed with the natural numbers crossed with the natural numbers. And I apologize, PowerPoint doesn't have a nice way of representing that set, but these are ends, or you can use your imagination that they're ends, consisting of the triples A, B, and C, where A, B, and C are members of the natural numbers with A less than B less than C. So which of the following are members of R? 1, 2, 3? Yeah. One is definitely less than two, which is definitely less than three. How about 2, 4, 3? Well, two is less than four, but three is four is not less than three. 3, 6, 9 would satisfy that as well, would satisfy the relation, but 2, 4, 3 does not because they're not in strictly ascending order. So the related question is, what is the degree of this relation? Well, the degree of that relation is 3. Okay, let R be a relation on the set of integers crossed with the set of integers crossed with the set of positive integers consisting of the triples A, B, M, where A, B, and M are a member of Zol, the integers. M is greater than or equal to 1, and A is equal to or congruent to B mod M. Which of the following of these are members? Well, um, 8 is congruent to 2 mod 3 because you get a remainder of 2 when you divide 8 by 3. Minus 1 is congruent to 9 mod 5 because you get 9 divided by or minus 1 divided by 5. You get a remainder of the minus 1. And I hate doing modulus operations involving negative numbers, but here we are. That one's a member. And the other one here is 1407. It always makes me pause, and I have to go through with paper. Sorry, I don't do that one quite easily off the top of my head. And the degree of this relation is again 3. There are 3 elements involved. The domains are the integers, and the positive integers. So let R be a relation consisting of 5 tuples, A, N, S, D, and T, representing airline flights, where A is the airline, N is the flight number, S is the starting city, D is the destination, and T is the departure time. So, for example, we could have Hawaiian Airlines Flight 392 starting in Honolulu and ending in Hilo, and its departure time is 7:22. Here, the degree of the relation is 5. And databases can help us to store these relations between various data sets, and they are a big business and a big topic in computer science. And it's a very competitive marketplace. This one is actually from Oracle. IBM used to have tons of nasty posters about Oracle that they would put up around the IBM lab. One of them said it was Oracle because Larry needs another boat, and that's probably likely still true. Actually, some microsystems went out of business in 2010, but here we are. So in a large database, you perform the same type of operations many times a day. So you might add records, delete records, update those records, search for them, and combine those records. There are several different types of database models out there, and probably the one that you've seen in lower division classes is putting together a file that's a flat file. There's also hierarchical databases, relational, object-oriented, and no SQL. So flat file databases resemble paper files and file cabinets, and they're pretty simple to create and access, but they can contain a lot of redundant information. You oftentimes see that in spreadsheets. Hierarchical databases relate tables in a parent-child format. Although this reduces redundancy, it's still a limiting way to handle data. Relational are the ones that link tables with common key fields, allowing for pretty sophisticated relationships between the tables. And the table links can be indexed or stored for future use, resulting in quicker searches. Object-oriented databases, these are not as popular nowadays, but they're structurally pretty similar to relational databases. And these are designed to store audio, video, or other mixed media objects. And you may have also heard of the term NoSQL, and it's an approach to database design that focuses on providing a mechanism for storage and retrieval of data that's modeled in means other than tabular relations that are used in relational databases. So for our relational databases, a database consists of records which are in tuples. These records are made up of fields, which are the entries of the n tuples. So here's one that I made for CS141 many years ago. And it's a database of student records that are represented as four tuples of the form student name, ID, major, and grade point average. And the relations used to represent databases are called tables. Each column represents an attribute of the database. So in a database, a primary key is when the value of that particular part of the n tuple uniquely determines the n tuple. And the domain is the primary key when no two n tuples in the relation have the same value of the domain. You often add or delete records in a database, but primary keys should remain primary keys regardless of whether you change something. So, for example, UH-Hilo, your student ID would be a primary key. We could use that to look you up, and it would uniquely identify you within some of our academic systems, such as STAR. The current collection of n tuples or records in a relation is called the extension of the relation, and the more permanent part of the database, including the name and attributes, is called the intension. Primary keys, again, should remain primary keys regardless of the extension. So in this example, I think I gave away the house a couple slides ago. Which of these domains are primary keys? And here the obvious one is ID number, since we have more folks that share names that come through UH-Hilo. For example, a common last name or a common first name. Certainly major is not a good one because we have more than one computer science major, and just saying, okay, it's a computer science major wouldn't identify that person. Same with GPA. You can imagine we have students that would have the same GPA, particularly if they were, first year and they'd gone through the first year and gotten all A's, we'd have a large number of 4.0 students. So that wouldn't allow us to uniquely identify someone. So in this case, student name is a primary key, and ID number is a primary key. If we're adding records in the future, I don't think I'd use student name as my primary key. Combinations of domains can also uniquely identify n tuples, and those are called composite keys. So if we looked at major field of study in GPA, in this table that I had as an example, that one would actually be a composite key, assuming that no new records were added to this database. Which of the following primary and composite keys from the previous examples make sense if you were adding more records? Well, I don't think student name makes sense because again, we can have members of a family that come through UH-Hilo, or people could just share very common names. Student ID would be a good one because that one's uniquely assigned. And major and GPA would not be good because we might have some students, several maybe, hopefully, computer science students that have 4.0 grade point averages, and that wouldn't allow us to uniquely identify them. So here, really only student ID works. So what operations can you do on N-ary relations? Well, there are a variety of them that can be used to form new N-ary relations or to answer questions on the database to find records that satisfy certain relations. So, for example, I may want to find all students with a GPA of 3.5 or higher in order to add them to the dean's list. So we'll let R be an N-ary relation and C be a condition that the elements in R may satisfy. The selection operator S sub C maps the N-ary relation R to the N-ary relation of all tuples from R that satisfy the condition C. So to find records of students with a computer science major, we use the selection SC1, where C1 is the condition major is equal to computer science. To find all students with the GPA greater than 3.5, we would use SC2, where C2 is the condition GPA is greater than 3.5. And then we can combine those two conditions to form SC3, where C3 is major of computer science and GPA is greater than 3.5. Projections are used to form new N-ary relations by deleting the same fields in every record. So the projection P, I1, I2, IM, where I1 through IM maps the tuple A1, AN to the M tuple AI1 to AIM, where M is less than N. P, I1, I2, IM deletes N minus N of the components of the N tuple, leaving only M components. So what happens when P13 is applied to the four tuples 2304, Jane Doe 234111001, geography 3.14, and A1, A2, A3, A4. So again, what we're doing is we're keeping just the first and the third record. So in the first one, we keep 20. In the second one, we keep Jane Doe geography, and then the third one, A1, A3. What happens when P14 is applied to table 1? This would basically remove columns 2 and 3 to produce table 2. So we would remove the ID number and the major, and we would be left with the student name along with their grade point average. Joins are used to combine two tables, and basically, here's the mathematical definition of that, and here's an example of where we would combine two different tables. So, for example, we might have a list of teaching assignments with professors and their departments and their course numbers. Looks like I'm teaching cryptozoology. Those are good courses. And then we have the class schedule, which indicates the course number, the room number, and the time. And so I can combine these two tables to get an entire teaching schedule. So here, we can see that I'm responsible for teaching cryptozoology 335. That's going to be field 1 because we're looking for Bigfoot at 9 a.m. But prior to that, we're checking out leprechauns at 8 o'clock in the morning. So if you're actually doing programming on relational databases, you'll undoubtedly encounter a language called SQL, which is structured query language. And it can be used with actual relational databases to carry out the operations described in this section, projections, joins, and selections. So here we might have a table of Hawaiian airline flights and go. You can tell I did this quite a while ago when I put that table together. And we want to find out how we can get to Lanai. There's a lot of flights there, popular destination these days. So, what is the output from select departure time from flights where the destination is equal to Lanai? Well, looks like we would be able to, depart at 8:47, 9:10, and 9:44. Again, it's a very popular destination, and I know that Go ceased operations, gosh, sometime around 2014. And if you're in class, I can tell you a story about Go. And SQL uses the term select to represent a projection rather than a selection operation. You can also make selections for more than one table, as shown in example 13, but there's even more. You can take 3 courses in databases at UH-Hilo and get a certificate in database development. Those are database internals, database systems design, database analytics, although I guess we've changed the title of CS422 slightly. Anyway, that's it for today's lecture on N-ary relations and databases. Thanks so much for coming along and sharing an adventure in discrete math today.